All right, so we're jumping all the way into chapter 6 now. So we're in section 6.4. And today we're going to solve first order linear differential equations. And I remember the first differential equations class I took, just the words differential equations sound intimidating, it sounds difficult. When we started doing it, it's one of those where it was like, really, this is it? That kind of thing. But I find them really fun. So just a couple of things, just introductory things about differential equations. First order means that the highest derivative. Well, let me back up just a little bit. Differential equation is just an equation that relates a function and its derivative, or derivatives. So it's some kind of relationship between functions and their derivatives. So we already know how to solve some differential equations. Something like y prime equals x squared is a differential equation. We have some kind of relationship with the derivative of a function, and here we don't have the function itself, but this is one type of differential equation. We talked in Calc II, we worked with separable differential equations, and that's a type of differential equation where you can get the y's on one side and the x's on the other side. So that would be something like dy dx equals xy. So we can rewrite this as dy over y equals x dx. We separated our variables, and we can integrate both sides to solve this one. So this is one that we have some familiarity with. Today we're going to talk about a little more complicated type of differential equation. So first order refers to the highest derivative. So the highest derivative in our equation is going to be the first derivative. Linear means that the power, the exponent on the function or its derivatives, the highest power is 1. So it's a linear equation. So we'll write a definition of a first order linear differential equation. Now I'm going to abbreviate. So our first order linear differential equation has the form dy dx plus p of xy equals q of x. And p and q are continuous functions of x. So p and q only depend on x, they have no dependency on y at all, and that's what part of what lets us work with these kinds of equations. And when we write it in this form, this dy dx plus p of xy equals q of x, this is called the standard form for a first order linear differential equation. So this is standard form. And if our equation is not in standard form, to work with them, we're going to want to put them into standard form first. So again, our first step, we rearrange, we put our differential equation in standard form so we can identify p of x and q of x from this form. And to solve it, we find what we call an integrating factor. Our integrating factor u of x is the e to the integral of p of x dx. So this is going to be one key in our solution of this differential equation. So we find this integrating factor, and then our solution, once we find our integrating factor, our general solution takes the form y equals 1 over u of x times the integral of q of x times u of x dx. So this is our solution. Once we put we have a first order linear differential equation. We put it in standard form. We identify p, we identify q. We come up with our integrating factor, e to the integral of p of x dx, and our general solution takes this form. Now, I'm going to explain why this works in just a second. We'll do an example and I'll explain why it works. I'm big on, rather than memorizing this formula, I like to understand why it works. If you understand why this works, you don't have to memorize the formula. You understand the process, and you won't have to memorize it. You can memorize this. This will always work to solve your first order linear differential equation. But once we do an example, I'll explain why the solution takes this form. If you understand the process, I find it much easier. And I read a quote once that says, a theorem in the head is worth two in the book. In other words, if you know how something works, it's worth having two different things written down. And I definitely tend to agree with that. So let's look at an example of solving a first order linear differential equation, and then we will look at why the solution takes this form. So here's our example. First order linear differential equations come up in lots of different contexts, in electricity, in all kinds of mechanics. You have relationships between the first derivative of a function and the function itself. So they, in terms of application, they come up in lots of different contexts. So we want to solve y prime minus 3y equals e to the 2x. And often you'll see differential equations written with prime notation rather than as dy dx. So first off, this problem's nice. It's already in standard form, so we don't have to rearrange anything. Sometimes we have to rearrange things to get it in standard form. So in this case, we need to identify p of x and q of x. So what is p of x? P of x is -3. And q of x is just e to the 2x. So we need to find our integrating factor. So u is e to the integral of p of x dx. So we just have -3 dx. And that gives us, and when we do this, when we find this integrating factor, we're not worrying about the constant of integration. We can conveniently ignore that constant of integration. We just want it doesn't alter our solution. So when we evaluate this, we get e to the -3x. So our integrating factor is e to the minus 3x. So then now we have everything we need to plug into our formula for the solution. So we plug that in, y equals 1 over e to the minus 3x times the integral of e to the 2x, that's my q of x, and I'll put this in parentheses, times e to the minus 3x, that's my u of x, dx. And what's that?
Do we solve that now?
Yeah, now we're going to simplify this. So 1 over e to the minus 3x is just e to the 3x. And we have the integral of e to the 2x times e to the minus 3x. So that's just e to the minus x dx. And here's where we need to be careful. We're multiplying, and this part is where we do need to keep careful track of the constant of integration, because we're multiplying by this e to the 3x out front. So this equals e to the 3x times the integral of e to the minus x is minus e to the minus x plus c. So in differential equations, often our constant of integration ends up being multiplied by a function. If you leave out that constant of integration, your solution is going to be completely wrong. And if I simplify this, I'm just going to distribute. So finally I get minus e to the 2x plus c e to the 3x.
Can we just replace that with a different constant, like C1?
You mean this whole quantity?
Yes, X, never mind.
Right. So we can't do that because we have this x in there. And we can determine c if we know the initial conditions for our differential equation. If we know that y equals such and such at x equals 0, that will determine our constant c. But this gives us our general solution for the differential equation. Everybody follow the process? The algorithm is pretty straightforward. Let's take a look at why this integrating factor, why the solution looks the way it does. The whys, I think, are always when it gets more interesting. So our equation is y prime plus, come on, where's my eraser? There you go. Plus p of x, y equals q of x. And our integrating factor, u is e to the integral of p of x dx. So what I'm going to do, this is our integrating factor, I'm going to multiply both sides of the equation by u, by the integrating factor. So I'm going to multiply the equation by u. So I get y prime e to the integral p of x dx plus, and I want to write this as p of x y e to the integral of p of x dx equals q of x times e to the integral p of x dx. Now I'm going to pause here for a second, and I want you, let's look at this side. Look at that for a second and see if you can figure out what that is. This is something that we're familiar with. Think about it for a second. What's that? Not a series. So let me give you a hint. Let me give you a hint. The derivative of the integral of p of x dx is p of x. Do you see it?
What's the derivative?
You're on the right track. So let me give you another hint. We have a derivative times a function plus a function times a, there you go. This is the chain rule. This is the chain rule. This is the derivative of a product. So it's the product rule, not the chain rule. Product rule. Right. This is the product rule. That's the product rule. So this is the derivative of a product. The product is y e to the p of x dx. So I'm going to rewrite this as y e to the integral p of x dx prime. The derivative of this product is this sum. And that equals q of x, and I'm going to just rewrite this as u of x. So now to solve this equation, I have on the right, I have just a function of x, and on the left I have a derivative. So I can integrate both sides. So when I integrate both sides, I get y times u of x equals the integral of q of x u of x. So I integrate both sides. So we integrate to get this, divide both sides by u of x, and I have the formula that we just talked about. So the way I normally go about solving these equations is I find my integrating factor, I find u, and then I multiply both sides of the equation by u and figure out what this product is. And usually it's pretty easy to pick out what this product is and then integrate both sides. Yes?
How do you know what u is? Where did that come from? That's a circular
are you asking how they figured it out initially, that would work?
Like, where did that come from? Yeah, where did they derive it? Circular proof, assuming this is true.
Right, assuming that is true. So, and this isn't a proof, this is just an illustration of why this integrating factor works to let us solve this. I'm not 100% certain who first came up with this technique and how they figured it out. My guess, usually the way it works with mathematics is someone sat down and started messing around and saying, what can I do with this to try to solve this? And maybe said, well, if I can make this kind of looks like the product rule, what can I do to make it into a derivative of a product? That's my guess as to how it happened. I can look into it a little more to see who came up with this. I'm not sure if it was even one person that came up with this technique. It might have been something that was developed kind of organically over a number of years. So sorry, that doesn't really help much, but a lot of times that's the way things work. So let's look at another example using this approach, recognizing that this is the derivative of a product. So our second example. And this one has another interesting little twist. So we want to solve x squared y prime plus 5xy plus 3x to the fifth equals 0. So this is our differential equation. It's a first order equation. Our highest derivative is 1. It's linear because the powers on the derivative and the function itself, y and y prime, are 1. So we need to put this in standard form. So our first step is standard form. So if I rewrite this in standard form, I'm just going to divide everything by x squared to get it into, or sorry, I'm going to subtract 3x to the fifth from both sides and then divide by x squared. Subtract 3x to the fifth and divide by x squared. So I get y prime plus 5 over x y equals minus 3x to the third. So I just subtracted 3x to the fifth and divided by x squared. So from this, I have p of x is 5 over x. Q of x is minus 3x to the third. So we need to find our integrating factor. Our integrating factor u equals e to the integral of p of x, 5 over x dx. And that is e to the 5 times the natural log of absolute value of x. And that's e to the natural log, I'm writing all my steps here, absolute value of x to the fifth, which is absolute value of x to the fifth. So I'm going to multiply both sides of the equation by absolute value of x to the fifth. I kind of don't like this absolute value, so let's think about what we can do here. If x is positive, x to the fifth equals the absolute value of x to the fifth, right? If x is negative, then x to the fifth is negative. I'm not looking at the absolute value. If x is negative, x to the fifth is negative. I'm multiplying every term in the equation by a negative quantity. So I just have everywhere I have a minus sign, I have a plus sign. Everywhere I have so I'm just changing the sign on every term. So that doesn't change anything. I could then multiply through by -1 and I'd be back to my original equation. So it doesn't really matter if I multiply by absolute value of x to the fifth or just x to the fifth, because we're multiplying every term, that it's not going to change the sign of anything. So what I'm just going to use, I'm going to multiply through by x to the fifth. Doesn't matter if x is positive or negative, I end up with the same thing. So multiply by x to the fifth. So I have x to the fifth y prime plus 5x to the fourth y equals minus 3x to the 8th. This quantity is, how can I rewrite this? I'll just write it in the opposite order. Yx to the fifth prime. That's the derivative of yx to the fifth. Equals minus 3x to the 8th. And now I integrate both sides to solve this. When I integrate both sides, that just undoes this derivative. So I get yx to the fifth equals the integral minus 3 integral x to the 8th dx. So yx to the fifth, finally, we're almost there, equals I'm sorry, what was it?
Negative 1/3.
Negative 1/3 x to the 9th plus c. Yes, sir. From here, I took the integral of both sides. Yeah, I integrated both sides. No problem. And I just eliminated that step here. So I would, if I were being more precise, I would write the integral of yx to the 5th prime dx equals the integral of minus 3x dx. Okay? Right. But so what I said was when I multiply through here, if x to the 5th, if x is positive, nothing changes. But if x to the 5th, if x is negative, I would end up with that would change the sign of everything. I would end up with a minus sign here, a minus sign here, and a plus sign there. So it changes the sign of everything. So it doesn't, and that's the same as what we started. Okay? All right. And now I just divide by x to the 5th. So y, finally, my general solution is minus 1/3 x to the 4th plus c over x to the 5th. And if we knew initial conditions, we could solve for our constant. So this method is the way I like to do it. I like to multiply through by the integrating factor and write this as a derivative of a product, rather than memorizing that formula. I don't care if you memorize the formula. I don't care if you write it on your note card. I just find this more satisfying. I feel like it's a little more, I understand a little more about what's going on. But where the integrating factor comes from, I've always wondered that. How did they figure that out? So I will look into that a little more. I've never read anything that says, Euler discovered this method in whatever year. It's always just presented as solve this equation by introducing this integrating factor. All right, any questions on first order linear differential equations? When you get second order differential equations and when you get nonlinear differential equations, things get much more complicated. But on Monday, we're going to talk about one form of nonlinear differential equations that we can transform into linear differential equation and then use this technique. So we'll add one more step on top of what we're doing here for one specific type of equation. All right, homework. Oh, that's a 5 and a 9, sorry. There you go.